Alright, before we continue our discussion on climate change, it's important to know the composition and the structure of the atmosphere. So air itself is not just a unique element or compound, but it is rather a mixture of many discrete gases, each with their own physical properties. So clean and dry air is composed of two main gases. Those are nitrogen, which occupies about 78% of the clean dry air, and then the second one is oxygen, which occupies about 21%. So these two gases have little to no effect on the weather phenomena itself, even though their abundance is obviously huge. It's close to 100%. Most of the remaining dry air that we have is made out of argon, and then there's tiny amounts of other gases, as you can see here on the slide. There's a little bit of all the other things that are listed. So CO2 itself is only present in about 0.04% of the air within the atmosphere, which is equivalent to about 400 parts per million. But even though it's in such a small percentage, it has very large effects on the heat that the Earth will experience, because it will absorb the heat that the Earth radiates towards the outer space. And we'll go through it in a bit. And thus, it will contribute to the heating of the atmosphere itself. So other gases and particles that the air contains are also important, and they vary from time to time, so from different years or decades or centuries, and they also decade from place to place. So geographically speaking, they will change as well. An example of these other gases are the ozone layer, for example. Water vapor will change from place to place and time to time, and also tiny solid and liquid particles, which we call aerosols. So water vapor, for example, are in quantities that vary from 0% to about 4% by volume on the atmosphere. And these quantities are clearly important because water vapor is ultimately the cause for cloud formation. And with this cloud formation, we receive precipitation in the land and in the ocean. However, water vapor, just like CO2, has the capacity to absorb heat energy that is radiated from Earth. And it also has the capacity to reflect some of the solar energy that is radiated out from the sun. So it is pretty influential when we look at the heating and the cooling of the atmosphere itself. The ozone layer, or ozone, is another important component of the atmosphere. Ozone is a form of oxygen which combines 3 different oxygens into each molecule, and it is not well distributed throughout the atmosphere. Most of the ozone actually lies in a zone at very high altitudes, in a layer of our atmosphere which is called the stratosphere, and we'll cover it in the next slide. So the presence of this ozone layer is pretty key to us Earth dwellers. The ozone is going to absorb the UV radiation from the sun, which makes it a type of kind of shield for the species that live on Earth. So without this shield, without this ozone layer, the Earth would be pretty much inhabitable for most of the life that is on Earth as we know it. Lastly, some of those solid and liquid particles, which we call aerosols, are also suspended within the atmosphere. So these tiny liquid and solid particles are suspended in the air and are a result of both natural but also some of the human processes. So some of the aerosols include sea salts from the breaking waters. They include fine soil that is blown into the atmosphere. They include smoke and soot from fires. They include pollen and microorganisms that are lifted up by the wind. And they can also include ash and dust from volcanic eruptions and other natural derived processes as well. So these tiny particles can be quite important. Some of them act as particles upon which the water vapor can condense in the atmosphere. And they can in fact act also as a shield from the sunlight. So many of them act as a reflector from the solar radiation that we receive, and hence they will have an effect to reduce the heat energy from the sun, so reduce the temperature of the lower atmosphere. So this is the reason why, for example, we see an episode of cooling that follows a volcanic eruption. Okay, so I think it's pretty obvious that the atmosphere itself starts at the Earth's surface and that it extends upward, but that the upper limit of the Earth's atmosphere is actually kind of unclear. So the atmosphere rapidly is going to thin out as you travel away from the Earth's surface, until there are just too few gas molecules to be detected. So first let's go ahead and look at the change in pressure with altitude. So this is going to be the graph you should be referring to. So atmospheric pressure itself is simply the weight of the air that is above. So at the sea level, the average pressure is just a little bit more than 1,000 millibars, which is 1 kilogram per centimeter squared. So as the altitude gets higher, the pressure will start to reduce because there is less overlying air to weigh on it. So that is why, for example, there is less pressure as you get higher and higher up in the mountains. All the way in Everest, which is the highest surface part of the Earth, the pressure is only 314 millibars. So about half of the atmosphere lies below an altitude of 5.6 kilometers, and about 90% of the atmosphere lies within the first 16 kilometers of the atmosphere, which is a very high percentage. So most of those gas molecules actually remain within that lower part of our atmosphere. And about 100 kilometers in altitude, when you reach 100 kilometers, only about 0.00003% of all of the gases that make up the atmosphere remain. So even beyond this altitude, however, there are still some trace gases which will gradually merge into the emptiness of the space, basically. So, okay, now let's go ahead and look at the changes in temperature with altitude. And in this case, you're going to refer to this graph. So the atmosphere is separated into 4 main layers, and each of these is subdivided on the basis of temperature. So it's going to be the troposphere, stratosphere, mesosphere, and thermosphere. So the first layer, which is the troposphere, is going to occupy the first 12 kilometers or so, but it also changes with seasons and with latitude. So in some areas it's going to be less than 12, some others is going to be greater than 12, again dependent on seasonality and on latitude. So in the troposphere itself is where most species reside, and it is characterized by the decrease in temperature with an increase in altitude until the upper limit of that troposphere, which is called the tropopause. So the average drop that you see in temperature as you get higher in altitude is of about 6.5 degrees Celsius per kilometer. So, for example, if we were at sea level and it was, let's say, 20 degrees Celsius, if we went to an altitude of 1,000 kilometers, it would only be 13.5 degrees Celsius. Okay? But again, this is going to also change through time slightly, and obviously through space. So those temperatures will differ greatly in tropical areas than they will in polar areas, and they will be seasonally driven as well, for example, in areas that have greater seasonality. So it is in this troposphere where most of the weather phenomena actually takes place. So meteorologists are typically concerned about measuring the changes in this sphere. To measure the changes in the temperature, the wind, the humidity, the pressure, we use things that are called radiosondes, which are instrument packages that are attached to weather balloons, and that transmit data by radio as it ascends through the atmosphere. So for example, my husband Marshall did an internship during his undergraduate school with the Montana State Geospatial Consortium, and he deployed these weather balloons containing the radiosondes, and these gathered the data, and he was helpful to analyze some of it that was collected by the radiosondes. Okay. The second layer as we rise upward in altitude is the stratosphere. So in the stratosphere, the temperatures remain relatively constant until a height of about 20 kilometers, where the temperatures start to actually rise about 2 degrees Celsius per kilometer of altitude gain. So this trend continues up until about 50 kilometers in altitude, and the temperature rise actually occurs thanks to the ozone layer. So the ozone layer, which as you can see in the image on the right here, is located around an altitude of 20 to 30 kilometers, will absorb the UV radiation and will hence warm the stratosphere that is above it. So this layer's upper limit is called the stratopause, again, close to the 50-kilometer mark or so. And from there onward, you have the mesosphere. So in the mesosphere, the temperatures begin to drop again until a height of about 80 kilometers above the surface. At this height, the temperatures approach about negative 90 degrees Celsius or so. So at this height of about 80 kilometers, is a boundary called the mesopause, which divides the mesosphere from the thermosphere. The outermost layer of the atmosphere, again, is the thermosphere, and it extends outward from the mesopause and has no really well-defined upper limit to it. It contains a very small amount of the Earth's atmospheric mass, so as we said, above 100 kilometers, only a tiny percentage of the gas remains. So it doesn't contain a lot of it. And here in the thermosphere, although the temperatures are very rapidly rising and reach actually up to 1,000 degrees Celsius, they are not temperatures that can actually be felt in the same way that we would feel the temperatures at the surface. So temperature itself is defined in terms of the speed at which particles move, and the temperatures in it themselves are incredibly high in the thermosphere because the particles are moving at incredibly high speeds. But because the gas particles are so sparse in the thermosphere, because there's so few of them, then that actual heat that they possess is rather insignificant to us. Okay, so now we're going to go ahead and cover radiation. So almost all of the energy that drives the Earth's weather and climate comes from the sun. The sun itself emits light and heat as well as UV rays that cause suntan or sunburns. So although these forms of energy make up a major portion of the total energy that radiates from the sun, they're only part of a very large array of energy, which we call radiation. Radiation is also referred to as electromagnetic radiation, okay? So this is depicted here by the image that you have on the bottom of the slide, and as you can see, there are many types of radiation, and all of them transmit energy through the vacuum of space at 300,000 kilometers per second, which is just a little bit slower in our atmosphere.